Section 6.1 Polynomial Functions. Our objectives are to classify polynomials, to model data using polynomial functions. If you remember from earlier in the year, we talked about specific terms, and remember that a monomial is an expression that is either a real number, a variable, or the product of real numbers and variables with whole number exponents. Now for this, some examples of monomials would be such as x, 103 would be a monomial, 17x squared, 5abc squared d, and 1/4. Remember that monomials means one term, so there would be no, after you combine like terms and everything, there would be no addition or subtraction signs in there. So the next thing we want to talk about is a polynomial. A polynomial is a monomial or the sum of monomials. So right here is the general form for a polynomial equation where a sub n and a sub 0 are real numbers. So the exponent of the variable in a term determines the degree of that term. And the standard form for a polynomial, when we write it that way, remember the terms are written in descending order by the degree. A one variable polynomial in standard form has no two terms with the same degree, since all terms have to be combined. They can have the same degree if you have more than one variable, but if it's a one variable equation, you shouldn't have more than the same term with the same degree because you would have to combine them together, is what that means. So for example, we have this polynomial equation right here. I know it's in standard form because I have this 2x cubed is my cubic term. My quadratic term is the negative 5x squared. The linear term would be negative 2x, and the constant term is 5. And so the cubic term, remember, has a degree equal to 3. The quadratic term's degree is equal to 2. The linear term degree is equal to 1, and the constant term's degree is 0, because it would be x to the 0 power. Remember, anything to 0 power is really equal to 1, so it's not really there. And this would be my equation in standard form because I don't have any, I have one variable in the equation, which is x. I don't have any terms that have the same degree, and they're in descending order, starting by the highest and going down to the lowest is what that means. The leading coefficient when you're in standard form is always the number in front of the term with the highest degree. So if this is the term with the highest degree, the number in front of that would be 2. So that would be called the leading coefficient. The degree of this polynomial equation would be the term with the highest degree as well. So the degree of this entire polynomial equation would be a degree of 3. So that's important to know how to find that. If you remember from before, we have filled out this chart that we have down in your paper. So the degree of a monomial or polynomial is the largest degree of any term of the polynomial. We already talked about that. Now for this chart, why don't you guys see if you can fill it out, and then so we want to hit pause, and then I'm going to talk about what each term means. So if you have this filled out, if you look at the first one, the number is 6. So 6 doesn't have any variables, so the degree is 0. And remember, when there's no variables, that means the name of the degree is a constant. The number of terms we have is 1, so it's a monomial. So the way that we would actually say this, we would call this entire term a constant monomial, because you always put the name of the degree first and then how many terms. So the next one, you notice that it's in standard form, and our x to the first power means the degree is 1. And then that means that if the degree is 1, it's called a linear for the name. And there's 2 terms, so it's a binomial. So this is called a linear binomial. For the next one, notice that we have 3x squared, which would be x to the second power means that the degree is 2, since there's no other terms. So degree 2 is quadratic, as we now know, and there are 1 terms. So if there's 1 term, then it's a monomial, so this would be called a quadratic monomial. And then for the next one, the highest term would be a degree of 3, so that's a degree 3, which is cubic. So cubic, 3 terms, trinomial. The next one has a degree of 4 with 2 terms, so it's a quadratic binomial. The next one, the highest term, is 5 for the degree, so that means the degree is 5, so it's called quintic. And it has 4 terms, so we call it a quintic polynomial or a quintic polynomial of 4 terms. Make sure you know how to find those names. Now, the next example is it says, write each polynomial in standard form, then classify it by its degree and number of terms. So the first thing you want to do is, of course, combine like terms if you can. Notice that this and this are like terms, so since they're like terms, we would want to combine those first to write it in standard form. So this gives me negative 2x plus 5. This negative 2x has a degree of 1, the 5 has a degree of 0, so it's in standard form. And if we want to write, classify it by degree and number of terms, this would be called a linear, because the degree is 1, binomial, because we have 2 terms, so linear, binomial. And again, that's because the degree is 1, and we have 2 terms. For the next one, same thing, you want to combine like terms. So this and this are like terms. We would end up with x cubed, and then we have plus x squared minus 4x. There is no constant here. So the highest term is 3, so we have 3, 2, and 1. That means this would be highest degree is 3, so cubic. There's 3 terms, so trinomial is how I would call that, and then that would be my standard form above it. For the next one, this is similar to the first one that we did. The only difference is that it's not in standard form. Negative 2x to the 5th plus 6 is how we would write it in standard form. So 5th power means it's a quintic, and 2 terms binomial. So make sure that you know how to do problems like this. Now for these, if I wanted to also look at what the leading coefficient was, which we didn't ask, so the leading coefficient for A would be negative 2. The leading coefficient for B would be 1 if it's not there, it's imaginary. Well, it's not imaginary, but it's there, but we just don't write it, is what I should say. And then the leading coefficient here would also be negative 2. The next thing we're going to do is we're going to model this kind of data. So remember that before, this r squared value we called the coefficient of determination. The closer the value is to 1 or negative 1, the better the fit the line is to the given data value. So you want to make sure you write that down, because that's important. That helps us find the models on our calculator for these this data that we're given. You've already used lines and parabolas to model data. Sometimes you can fit data more closely by using a polynomial model of degree 3 or greater. So if you just look in general, we have these different data values. And we did the linear regression on the calculator for a line, and that's what we got. Then I did a quadratic, and then I did a cubic model. So for this, notice that the cubic model goes through more of the points. So which one would probably be the best model to use? It would be the cubic. And the way that you can tell is by using that r squared value, and I'm going to again show you guys how to do that. Now for this, cubic equations are generally in the shape of this. So this would be the general shape of a cubic, or it could go like this. So that's what a general cubic equation looks like, and we'll talk about that in the next section. Use your calculator to determine whether a linear model, quadratic model, or cubic model best fits the values in the table. So let's go ahead and get our calculators up, and you guys should also get your calculator up. And on my calculator, oops, I'm going to first have to plug this into my stat plot. So if I plug this into my stat plot, we go to stat, enter and edit, and of course you guys should also get out your calculator and do this with me so that you become familiar with the process of doing this. If you have something in there that you don't want, remember you highlight the list, hit clear, and push down. Don't hit delete because it'll delete the list. Then I'm going to enter the values that I have. So I already have my y values. I just need to enter the x values. So I have 0, 5, 10, 15, and 20. So those are my x values for list 1. My y values are already in list 2. Now, remember to get the equations, we go to stat, right arrow to calculate, and I want to see if a linear model, quadratic model, or cubic model is best fit. Now, I need to first go down to linear, because I'm going to do that one. So the linear model comes up like this, and if I hit enter, notice that this is what I get. So to tell which one's going to be the best fit, I'm going to use that r squared value to help me. So over here, I'm going to write down the values that I need. So we have linear. So the linear r squared value was equal to 0.5538. So 0.5538. If you don't have the r squared value on your calculator, every time you clear your calculator memory, you have to put it back in. So to get that r squared, if you don't have it, hit second 0, which takes you to your catalog. And then if you hit this button right here, which is your underneath math, so if you hit that button, it scrolls you to the D's. And if you scroll down to diagnostic on, it's going to turn those values on for you. So hit here, hit enter, and hit enter again. That's going to turn it on. So if you didn't have it, do that, and then it'll turn your diagnostics on for the r squared value. Now we did linear, so now I want to do stat, calculate. I want to do quadratic regression, which is number 5, and look at the r squared value. So my quadratic regression, I get 0.7631 if I round. So quadratic, the r squared value, oops, I should write r squared. I'll just make this bigger. Oops. So the quadratic r squared value is equal to 0.7631. And then we want to do the last value, which is going to be our cubic. So stat, calculate, and then notice number 6 right underneath of that is cubic. So if I hit 6 and enter, I get an r squared value. And notice that for this, it's 0.9998. And since it's 0.9998, that tells me that this is the closest one to 1 or negative 1. Therefore, the cubic model is going to be the best. So the cubic r squared is equal to 0.9998. And again, that means I'm going to use the cubic model. So then the next thing I want to do is write all these values down. So the a value goes with your cubic term, the b value with your quadratic, c is for your linear, and d is for your constant. So usually I round to the nearest hundredths, 2 decimals. Y equals negative 0.01x cubed plus 0.43x squared minus 3.30x plus 10.08. I forgot the 0 there, so I should change that to 0.8. And then, of course, the cubic model is the best fit because it's the closest value to 1. If I look at my calculator, remember I can graph these all together if I wanted to. If I turn my stat plot on, second y equals, and go to the first stat plot and turn it on. And remember, you can hit zoom 9, gives you a nice stat plot, which says zoom stat. So if I hit zoom 9, I get a nice stat plot. Here's my data. And if I wanted to, I could enter my linear, quadratic, and cubic equation. So I'm going to do that real quick. So stat, calculate, number 4. If I go to vars, y1, oops. Let's try that again. So vars, y function, y1, enter, and that puts it in my y equals right there. So now I'm going to enter the quadratic equation into my y2, so stat, calculate, quadratic, Oops, I did cubic, so I'll do this into y3 vars, y vars, function y3, because I want to do my quadratic in the other one. Enter. And then stat calculate number 5 vars, y vars, function. I'm going to put it in y2. Enter. So that puts all my equations into my y equals for me. And if I hit graph, it'll graph all three. So that was the line. The next is going to be my quadratic if I graph it. So if I go to my y equals and turn that on, and I'm going to turn on the cubic as well and hit graph. So that was my linear. I don't know why it's not graphing my y2. So this would be quadratic. And then if I go back to my y equals, it usually graphs them all together. I don't know why my calculator is not working right now, but that's okay. We can just look at it individually. And then that would be the cubic. And notice the cubic goes through most of the points. That's why my r squared was the closest to 1, and that's why it's the best fit model. So what I suggest you guys do is to hit pause in the video and see if you can do B on your own, and while you're doing B, I am also going to do B. So I plug everything into my stat, enter and edit list 1 and list 2, and then I did my linear regression, and my r squared is what I got in the screen that I just had, so I'm going to write that down. And these are your linear, quadratic, and cubic r squared terms, and when you do this, you find out that the best fit is the cubic because r squared is the closest to 1, and then if you write down your equation, this is the equation that you should get for that. So let's do this one last problem. The table below shows the world gold production for several years. Find a quartic function to model the data. Let 0 correspond to 1975. Estimate the production in 1988. So we want a quartic model. That means degree of 4. And we're letting 0 correspond to 1975. So this would be 0, 5, 10, 15, 20, and 25. How do I get those values? If I do 1980 minus 1975, it's 5. 1985 minus 1975 is 10, and so on. Then I'm going to plug this into my calculator stat plot. So I'm doing this, you guys are doing this. Stat, enter. Up and clear my list. So I have 0, 5, 10, oopsies. Stat, enter. Clear down. So 0, 5, 10, 15, 20, and 25. Oops. And then list 2. $38.5, 39.2, 43, oops, 43.3, 70.2, and 82.6. And I just noticed that those values didn't clear, so I'm going to just delete them out. And we are missing a value, 38.5, 39.2, 43.3, 70.2. I'm missing 71.8. All right. So I always make sure to check when I'm doing this to see that I plugged in the values correctly. Most often mistakes are made because they're plugged in incorrectly into your stat plot. So now that I did that, I'm going to go to stat, calculate, and we want a, notice number 7 is quartic, so number 7. And enter. See this arrow down here? If I hit this down arrow, it gives me my r squared value, which is 0.95277, etc., which is a pretty good model for the data. And so these give me all the values. If I scroll back up, I can get my A value. So this is going to give me my equation that I need. So you should write that down. I'm going to write down in just a minute. And I'm also going to put this into my y equals. So I'm going to clear out all the stuff that I have in here right now. So clear that out. So if I go to my home screen, second mode, stat, calculate, number 7. I'm going to put it into vars, y vars, function y1. All right, so I'm going to write down this equation that I have. So y equals 0.0005 x to the 4th minus 0.03 x cubed plus 0.74 x squared minus 3.47 x plus 39.10. If the front starts with a bunch of zeros, I always usually go to the first number, which is why I did that. And if you look at your calculator, notice that it didn't show that, but since it says e to the -4, that's how I know I'm timesing this by 10 to the -4th power, which means I'm moving this decimal place 4 places to the left, which is where I get that 0.0005 x to the 4th. So make sure you watch out for those, as we saw in the other chapter. And we want to estimate the production in 1988. So since x equals 0 corresponds to 1975. If I want to find 1988, I would do 1988 minus 1975, which gives me an x value of 13. So I can plug 13 into this equation here, which is going to give me some rounding error since I rounded it. That's why I plugged it into my y equals into my calculator. So since I did that stat vars, y vars, I can just go to second graph, which gives me my table. Oops, I changed this from my other class, so I'm going to fix that. So going to my table, if I go to 13, I can get what the production level is going to be in 1988. So 58.59. And remember, this is in millions of troy ounces. So the Y value would be 58.59 millions of troy ounces. Now, of course, like I said, you could just plug 13 in for x into your actual equation. That's fine as well. It's just going to give you some rounding error, but it's okay to do that.